This is an overview of our paper titled Brave, Broadening the Visual Encoding of Vision Language Models. Vision language models, or VLMs, are typically composed of a vision encoder and a language model which are connected by a bridge network. From a given input image, the VLM extracts features using the vision encoder. The features are processed by the bridge network and then given to the language model to output predictions for downstream tasks, such as captioning or visual question answering. In other words, the role of the bridge is to get the vision encoder output and transform it into an input that the language model understands. Here, the model produces an accurate caption for the given image with 2 giraffes. Recently, we have seen a remarkable progress in VLMs thanks to the several methods proposed such as Flamingo, Blip2, InstructBlip, Lava, Poly, and so on. However, despite the progress, VLMs are still subject to several shortcomings. On the language side, the language models are known to be susceptible to hallucinations and logical errors. On the vision side, VLMs are similarly limited by the visual understanding capabilities of vision encoders they use. The limitations include blindness issues against certain image features and visual hallucinations. In this work, we focus on the visual aspect of VLMs and investigate these visual understanding issues. Let's look at an example from a VLM benchmark. We are testing the predictions from 2 recent VLM methods, namely InstructBlip and Lava. For this image pair, we ask the following question. Is there a hand using the mouse in this image? The answer is obviously yes for the first image and no for the second. Note that the VLMs see each image independently and make predictions. We then assess whether they are able to differentiate the visual differences between the 2 images. As you can see, InstructBlip can correctly answer for both cases, meaning that it can differentiate the visual difference between the 2 images. However, Lava fails to do so and answers as no for both images. Another example, we ask, are the butterfly's feet visible? This time InstructBlip fails to differentiate while Lava succeeds. Finally, if we ask, is the door of the truck open? Both methods fail to differentiate 2 images. Note that in all cases, the question is easily answerable by a human, yet the models fail to perform consistently well. Also note that these methods employ different vision encoders, namely EVA and CLIP, so they are likely extracting different representations of the images. However, neither of the encoders can consistently extract the relevant visual features to answer the question. In this paper, we propose a new method which we named as Brave that can consistently perform better than the recent methods. Brave aims to broaden the visual encoding capabilities of VLMs. This is based on a well-known property of different representations in machine learning. They can yield different generalization properties, and each can play a role when ensembled to create a more complete representation. Inspired by this, we first perform a benchmarking of several vision encoders with different biases such as training data, objective, and model size to study their generalization properties when used in VLMs. Based on our findings, we introduce the Brave method that can efficiently consolidate features from any number of vision encoders into a compressed and contextual representation, leading to state-of-the-art performance. By leveraging the diversity in visual representations, Brave can significantly push the state-of-the-art for a broad range of captioning and visual question answering benchmarks, as you can see in the spider chart. Finally, we perform a comprehensive ablation study of Brave, which we hope provide useful insights to the researchers. Let's start with benchmarking vision encoders. Using a standard architecture, we train and evaluate VLMs by only changing their vision encoders. We consider several vision encoders with different inductive biases stemming from their differences in training objectives such as masked image modeling or image-text contrastive learning and datasets such as Lion or JFT. We also consider model sizes ranging from a few hundred millions to a few billions of parameters. In total, we benchmarked 8 different vision encoders including CLIP, Dino V2, VITE, and more on several vision language tasks. While we defer the detailed results and takeaways to the main paper for brevity, we note the following two key observations. We observe that there is no single vision encoder that can perform consistently well for different captioning and visual question answering tasks, suggesting that using a single encoder in a VLM is inherently limited. Furthermore, we observe that the encoders with different biases can perform surprisingly similar, suggesting that there could be multiple cues that can be leveraged to solve the tasks. Our findings motivated us to ask the following question. Can we broaden the visual capabilities of VLMs through combining vision encoders with different biases? We answer positively and introduce Brave to achieve this efficiently. This is an overview of Brave framework. Please see the paper for details. At a high level, this is how it works. First, the visual features from several frozen vision encoders are extracted. Then, these are linearly projected to the same dimension and concatenated sequence-wise. We would like to combine the concatenated visual features to get a better representation. To achieve this in a scalable way, we introduce multi-encoder querying transformer, or MEQ-former. It is a transformer module that interacts with the visual features through cross-attention layers, thus resampling them. We show that the MEQ-former effectively compresses and consolidates diverse visual features. It takes as input a set of learnable queries and a text prompt specifying the vision language task to extract better task-aligned visual features. Finally, the combined resampled features are fed as a visual prompt to a frozen language model. Using the visual and textual prompts, the language model outputs a text prediction. During pre-training, we keep all the vision encoders and the language model frozen. This results in training only 1% of all the parameters, leading to an efficient training. Furthermore, the output of MEQ-former is a fixed-size vector, enabling the method to scale to several vision encoders efficiently for a more complete representation. We show that Brave achieves state-of-the-art performance for a broad range of vision language tasks. This includes COCO captioning, no-caps novel object captioning, VQA-V2 general visual question answering, OGVQA, which requires external world knowledge to answer the questions, GQA that measures spatial reasoning capabilities, and VisWisQA that has questions from people who are blind. As summarized, all these benchmarks evaluate different aspects of VLMs, which is important to understand their strengths and weaknesses. Furthermore, Brave significantly improves robustness against visual hallucinations and blindness issues as measured by the POPE and MMVP benchmarks. As you can see at the left, POPE can probe visual hallucination tendencies by asking for objects that do not exist in the image. On the other hand, MMVP at the right has image pairs with some visual differences. Their results show that these visual differences can be challenging for recent VLMs to pinpoint. In other words, they exhibit blindness to changes between the images. All of these are achieved while using an order of less trainable parameters than the existing methods during pre-training. Quantitatively, results on captioning benchmarks show the significant improvements achieved by Brave. It achieves the best results on no-caps evaluation sets for both out-of-domain and overall benchmarks. For COCO captioning, Brave achieves the second best result after Pali while using significantly less trainable parameters, pre-training data, and image resolution. Please see the paper for details and comparisons. Similarly, for visual question answering, Brave achieves strong results across the board. Notably, Brave obtains the best performance for 6 out of the 7 evaluations and second best for VQA-V2. Similar to the captioning, this is achieved while having a lower sample complexity than Pali. Please see the paper for a closer look at the performance. Furthermore, Brave improves the performance for benchmarks measuring robustness issues of VLMs such as MMVP and POPE by leveraging diverse visual features. Qualitatively, Brave achieves consistent improvements for a wide set of visually challenging inputs compared to recent methods as well as single encoder baselines. Please see the paper and supplementary for more results. Furthermore, Brave predicts accurate descriptions for a diverse set of inputs with visual abstractions, novel classes, and fine-grained details. The examples are from NoCap's validation set. Let's look at some example predictions. A plate of French toast with strawberries and powdered sugar. A topiary in the shape of a lion with yellow flowers. 2 towels shaped into swans on a bed. You can pause the video to examine the others. Next, we provide a detailed analysis of Brave in different aspects in the paper. This includes several ablations such as training data, model components, fine-tuning, and so on. Furthermore, we perform an in-depth analysis of contribution of each vision encoder to the final performance. Finally, we provide a detailed discussion of limitations and interesting future directions of our work. Again, please see the paper and supplementary material for details and takeaways. To conclude, our results highlight the potential of incorporating different visual biases for a more broad and contextualized visual understanding of VLMs, opening a promising direction for further research. Thank you for your attention.